Hello guys, welcome back to my YouTube channel Anveshana Academy. This is Dr. Manjunath Chennapugod. Dear students, in the previous class we discussed what is thermal conductivity and how to calculate the thermal conductivity and what is the thermal conductivity for metals and non-metals. Okay, and what are the factors they are going to influence on thermal conductivity in detail with some examples we discussed. And also at the last we discussed how to calculate or how to determine the thermal conductivity of the given material. That experiment also we have discussed. Okay, dear students, come, we'll move towards next topic. So that is numerical number 2. Dear students, what I will do, I will try to take one numerical and I will try to solve one numerical on conduction heat transfer by using Fourier's law of conduction equation. So dear students, so first what I will do, I will read the problem. What is that? That you can see here now, dear students. Okay, example 2. Calculate the rate of heat transfer per unit area through a copper plate 45 mm thick whose one face is maintained at 350 degrees Celsius and other face at 50 degrees Celsius. Take thermal conductivity of copper as 370 watt per meter degree Celsius. Dear students, so he has given some data. What are the things he has given? He is telling that there is a copper plate. Yes, there is a copper plate. Yes, I mentioned here. Now he has taken a copper plate and that copper plate having a thickness, that thickness I will mark here as a 45 mm he has given. Yes, 45 mm thick copper plate is there and one end of that copper plate is 350 degrees Celsius. Okay, and another end of the copper plate is 50 degrees Celsius. When there is a change in temperature, right, what we can say now? The heat is going to transfer from 350 to 50 degrees Celsius. And that having that plate having a thermal conductivity, that thermal conductivity I will represent here as a K. That K also he has given as a 370 watt per meter degree Celsius, dear students. This is a actual picture of the copper plate we can see. Then what we have to do, dear students, before solving the numericals, we need to draw the schematic diagram for a particular problem. So I will take a 3D view here now. So then it is a copper plate. So it is a copper plate. You can mark here now schematic diagram. I will mark here as a copper plate. Okay, fine. Then here it is a high temperature region. So high temperature region, what I will do, left to right, I will take high will my left and low temperature will be my right. Actually heat is going to transfer from high temperature to low temperature. So high temperature region I will mark here as a T1, then low temperature region I will mark here as a T2. Heat is going to transfer from T1 to T2, so that heat I will represent here as a Q, dear students. The notation I will give here Q. Then that plate having a thickness, that thickness I will mark here as a L. So starting point I will mark here as x1. So then end point of the plate I will mark here as a x2. So x2 minus x1 will be the total thickness of the copper plate what he has given. The same thing, that what I will do, I will draw the front view of this now. So what I will do here now, dear students, T1, you can take capital T or small t, I will take it capital T. So T1 is equal to 350 degrees Celsius. Then T2 is equal to 50 degrees Celsius. It is a copper plate. Yes, I mentioned that copper plate having a thermal conductivity, that is K, and thickness of that copper plate is L, that is equal to 45 mm he has given, dear students. Okay, so now what I have to do then? Now I will list out the given data. So I will list out the given data. What all things he has given? L is equal to, he has given, so 45 mm thick he has given. So I will write it here 45 mm thick. So then that 45 mm I will convert it into meter. Then 45 mm divided by 1000, I am going to get meter, that is 0.45 meter, dear students. Okay, fine. Next he has given one face is maintained at 350 degrees Celsius. I already marked here. Then the temperature I will mark here as a T1. The T1 is equal to 350 degrees Celsius, dear students. Or you can convert it into Kelvin also. But thermal conductivity has given in terms of watt per meter degree Celsius. So therefore what I will do, I will not convert this degree Celsius into Kelvin. I will keep it as it is. Okay. The next T2 is equal to how much he has given? He has given 50 degrees Celsius. Yes, 50 degrees Celsius he has given. Then thermal conductivity, what is the notation for thermal conductivity? That is K. How much he has given? He has given 370 watt per meter degree Celsius he has given. This is a given data, dear students. Now with the help of this given data, what actually is asking to calculate the thermal conductivity of, calculate the rate of heat transfer per unit area. Rate of heat transfer per unit area is nothing but what? That is small q. The rate of heat transfer per unit area is, that is small q, that is heat flux. That is nothing but what? Capital Q divided by A, dear students. So now we know already from Fourier's equation. So from Fourier's law, we know that conduction equation. What is that conduction equation? That is capital Q is equal to minus Ka into dt by dx, dear students. Okay, so now what is dt? Change in temperature. So then what I will do now? I want to calculate the rate of heat transfer per unit area. So for that purpose, what I will do? I will rearrange this equation now. So therefore Q is equal to Q by A. So that A I will take it into left side. So therefore Q by A, that is small q, is equal to, what is left out then? Then is equal to minus K into dt by dx, dear students. Okay, so what is minus K? So what is change in temperature? Generally how we will write, dear students? Final temperature minus initial temperature. That is nothing but what? Change in temperature. I will write it here now. What is final temperature? That is T2, because my starting point is here and end point is here. The initial point and end point. So final point, that is temperature at final point is T2 minus initial temperature is T1. So divided by what? I will write it here dx. What I have taken dx? Dx I have taken it here L actually. So that is what? L. That is L is, I will write it here now. Dear students, what I will do? I will do some small changes here now. T1 I will take it this side. Then what happens? This minus T1, this minus K will become plus. So therefore what I can write? I will write it here now. K into T1 minus T2 divided by L. So this is nothing but what? So heat transfer per unit area, that is what? Small q is equal to K into T1 minus T2 divided by L. So fine. Now what I will do? I will substitute the value. Simple. What is K is equal to? K is already given. That is 370. I will write it here. The next T1 is equal to how much? T1 he has given here 350 degrees Celsius. I will substitute 350 degrees Celsius. Fine. Minus how much? T2? T2 he has given here 50 degrees Celsius. I will write it here 50 degree Celsius. Then divided by what is the L? L is equal to thickness of the plate, that is 45 mm he has given. Converted into into meter is what? 0.45. So I will do it here now. So then what I will do, dear students? I will try to substitute now. What I will do here now? So what I can do? So what I will do? 370 into okay. So now 350 minus 50 into bracket, the next 0.045. What is the answer? That is 1 minute, sorry. So Q is equal to how much it is? 2456 is there. Then what I will do, dear students? I will convert it into, then what I can write now? Can I write it in terms of mega watt per meter square? How much it is now? So I will divide it by, so that is 2.466 mega watt per meter square. This is what? This is the heat flux in that particular plate. This is my final answer, dear students. So how you got the watt per meter square? Yes, you can see that also. So what is Q? You can got it here, right? What is K here now? This is the equation, right? So what is Q is equal to, you have written K into delta T divided by L. So I will write the unit. What is unit for K? Watt per, here in this problem, meter degree Celsius, into what is change in temperature? That is degree Celsius. What is that? Is meter. So then what happens now, dear students? You can see here now, degree Celsius will get cancelled. Then what is going to left out? So at the numerator side you are going to get watt. Then at denominator side meter is there. You are going to get a meter square. Hence the heat flux is equal to rate of heat transfer per unit area. That is how much? Small q is equal to 2.466 megawatt per meter square, dear students. This is how to solve the numerical. Thank you.